Hello everyone! Thank you for attending the BAS Electrochemical Webinar 2022 December. I'm Miho from International Sales Team, and I will be the moderator. Today, it will be the third lecture of a series of lectures in the field of coordination chemistry and electrochemistry, introducing basic electrochemical methods and electrochemical applications with a focus on organic complexes, introduced by Professor Masa-aki Haga from Chuo University. Today's theme is coordination chemistry and electrochemistry, cyclic voltammetry, and reaction mechanism at Electrode, Part 2.
Good afternoon. This is Masa-aki Haga of this lecture. This is the third lecture on cyclic voltammogram and electrochemical reaction mechanism at the electrode. Today, I deal with more complicated electrode reaction, such as ECE or ECEC mechanism, and also electrocatalyst at the electrode. First of all, I started with the reviewing last lectures, in particular cyclic voltammogram methodologies. Cyclic voltammetry is a non-steady state method to investigate reactions at the electrode surface. By using the three electrode systems, as shown here, the experiment records the current flowing through the working electrode when a triangular-shaped potential is applied to the working electrode, and a plot of current versus potentials is constructed, which is known as the voltammograms. The obtained current response provides us a lot of information about the stability of redox species. Two typical CV responses as shown here, reversible and irreversible CV. The reaction schemes are labeled by a string of letters signifying the reaction steps. Here, the E represents an electron transfer at the electrode surface, and the C represents the homogeneous chemical reaction. So, ECE mechanism refers to an electrode reaction in which the product produced by electron transfer is immediately converted to Z by chemical reactions. Once the electron transfer of analyte occurred at the electrode, there are several follow-up homogeneous chemical reaction pathways, which is summarized in these figures. We have already discussed about the reversible E and EC mechanism. So in these lectures, I deal with ECE and EE and catalytic mechanisms. In ECE process, the product C generated by the EC process is further reduced to the species D. This is called ECE mechanism. In EE mechanism, the successive one electron transfer occurred and resulting reduced species B further reduced to a species C. We call it EE mechanism. In special type of EC mechanism, the species Q, which is electroinactive, react with the electroproduct B to regenerate the sterling A. As a result, the species Q is converted to P by the electron mediation of AB coupled. This is called catalytic mechanism. Each mechanism shows characteristic diagrams, so we can judge what kind of electrode reaction occurred from CV shape. In ECE mechanism, the starting A is converted C after the ECE mechanism, and C is further reduced to the another species D. The voltammogram shape is varied by the E1 and E2 potential values, also the relevant kinetic parameter lambda. Here shows how the CV shape change with increasing lambda values, which mean the faster reaction rate K. Let us consider two cases. First case, shown in A, is that the C is more easily reduced than A, which means E2 is greater than E1. For lambda equals 0, that is slower chemical reaction rate K, a simple one-electron reversible CV is obtained. The V oxidation peak decreased as the lambda value increased, that is, the chemical reaction rate increased. With this change, the oxidation peak C grows with increasing the lambda values. The second case, B, where the C is less easily reduced than A. For lambda equals 0, this is the slower chemical reaction rate. Only A-B couple waves is seen. When the lambda value increased, which means the following reaction rate become faster, as the more negative potential the CD couple wave appeared and increased with increasing the lambda values. At the same time, the oxidation wave of B decreased, resulting in the loss of reverse oxidation peak A. Therefore, ECE mechanism, both redox potential of AB and CD couples and the kinetic parameters lambda play an important role for the CV shape. The first example for ECE mechanism, I pick up the geometrical isomerization of cis-bis diphenylphosphenol ethane bis carbonyl molybdenum 0 by electrochemical oxidations. This paper was published in 1974, an old paper. However, it is a typical textbook example, so I take it up. In the voltammogram, in this figure, please note the y-axis is taken different. The anodic current is plotted on negative side. Anyway, the oxidation of cis-molybdenum complex takes place at around plus 0.3 volt, shown OX1. No corresponding reduction peak was observed. Instead, the new reduction peak RED2 appeared at minus 0.1 volt, and corresponding anodic peak OX2 was seen. The new peak comes from the redox couple of trans-molybdenum complex, which is clarified by another experiment. Therefore, the electrochemical oxidation of cis-molybdenum complex is accompanied by the cis-trans isomerization. Since the starting molybdenum 0 complex has the D6 electronic configurations and kinetically stable. But once molybdenum 0 is oxidized to molybdenum 1 state, which is D5 electronic configuration, therefore the kinetically labile, which lead to the fast cis-trans isomerization. The second example is another organometallic iridium complex containing pentamethyl cyclopentadienyl ligand and bidentate methyl thiophenyl imino also benzoquinone ligand to coordinated iridium-3. This is abbreviated in iridium Cp*Q. Iminocatechoate is known as a non-innocent ligand and acts as a multi-electron reservoir as shown here. When the potential is scanned to the positive direction from -0.0 volt to 0.6 volt, two oxidation peaks at -0.06 volt and 0.3 volt are observed. The one electron oxidized form after the irreversible process OX1 show a reversible second oxidation OX2. When the scanning potential is inverted at 0 volt after the first oxidation OX1 and scanned to the negative potential directions, Ni peak is observed at the -0.5 volt. Surprisingly, the X-ray structures of isolated one-electron oxide complex iridium Cp*Q+ show a tridentate ONS coordination mode, and the Cb of isolated oxide product exhibit reversible oxidation at +0.26 volt, and the potential scan from 0 volt to -1 volt, reduction peak at 0.5 and the corresponding anodic peak at -0.1 volt. This Cb behavior is identical to the Cb response of iridium Cp*Q complex, which bidentate NO coordination mode. Therefore, the reduction of iridium Cp*Q+ induced the structural rearrangement from iridium ONS mode to iridium NO bidentate mode through ECEC mechanism. To summarize the Cb behavior, considering with the structure change, the bidentate iridium complex is first oxidized the monocation complex, which undergoes structure isomerization to a tridentate coordination mode, followed by further oxidation to a dication complex at OX2 peak. For the reverse scan to the negative potential directions, dication complex is reversibly reduced at RED1 peak to a monocation complex. Further being reduced to a neutral complex, simultaneously a structure change occurred from tridentate coordination mode to a bidentate mode, and returned to the original structures. Therefore, the ECEC mechanism is observed in the electron transfer process, accompanied this structure's change as a chemical reactions. At the first glance, the voltammogram may seem complicated, but it can be explained by considering the structure change. We move to the EE mechanism for multi-step electron transfer process. Please consider the two-step one electron reduction of A. When both electron transfer fast enough compared to the mass transport, the Cv safe is determined by the potential E1 and E2 and potential difference delta E. When delta E is positive, the second reduction occurred much more easy than the first one, and we observe the single wave is indistinguishable from a Nernstian 2E transfer. Since simultaneous two-electron transfer is unlikely, the reaction occurred in two steps, with second electron transfer followed immediately after the first electron transfer. When the delta E is less than minus 125 millivolt, two waves becoming dissolved to two well-separated waves, and each wave takes on characteristic of one electron transfer. Here I show you two examples of EE process, both of which two redox-active moieties are connected with different organic connectors. The first example is C mediator of 99-diacetyl alkanes with different methylene chain lengths N. As methylene chain length N is larger, the voltammograms show a decreasing repulsive interactions, and delta is approaching to zero or positive values. So the CB exhibit 1, 2 electron waves. The second example is dinuclear molybdenum tetracarbonyl complex with bridging alpha-alpha-pyridine imine ligand. When the two pyridine imines are directly connected in dinuclear molybdenum complex, two well-separated one electron reduction waves are observed. But when diphenyl connecting group is inserted into molybdenum, the interaction decreases, which lead to the one-step two electron wave. Let's consider the successive electron transfer from the viewpoint of the molecular orbital in the molecules. When a single molecular orbital accepted an electron by successive one electron in a molecule R, two well-separated waves are expected because of the strong electrostatic repulsion between electrons. However, in the electron transfer event, on the two different A moieties, first electron is added into one of A groups, and the second electron is required to more energies, which depend on the extent of the interaction between two A groups. Even the case of no interaction between two groups, the statistical factors makes the second electron transfer slightly more difficult, and delta E shows small negative values as shown in these equations. In the EE reaction at the electrode, we have to consider the possibility of disproportionation or comproportionation equilibrium, which occurred in the solution near the electrode. The extent of the reaction is governed by the potential difference. When two well-separated waves are observed, disproportionation constant K(dis) is small, and the equilibrium reactions lie to the left. In EE process, the comproportionation constant Kcom, which is obtained from the delta E and reciprocal of K(dis), is often used to the measure of the stability of mixed valence state. The mixed valence compound shows interesting physical properties such as conductivity or optical properties. Therefore, electrochemical measurement has been used in many studies to evaluate the stability of mixed valence complex. In EE process, sometimes ion pairing effect induce a large effect on delta E values because successive reductions increase the analyte charge. Here shows the CB of this frivolent dinickel upon the charge change of supporting electrolyte from TBA chloride, TBA PF6, and TBA perfluorophenyl borate. the dramatic increase in delta E is observed from 200 mV up to 850 mV. Not only the electrolyte but also solvent affect the delta E. When the solvation becomes stronger from dichromethane to DMSO, the effect of the electrolyte change on delta E becomes smaller. Therefore, the charge change by EE process affect the solvation and ion pairing of the analyte, which reflect on the potential difference delta E. Copper dinuclear complex shows a reductive EE process, but the electrode behavior is strongly dependent on the ligand structures. These two copper complexes have a bis-mu hydroxy bridge structures. However, the CuDA-Na dinuclear complex show one-step 2-electron waves. On the other hand, CO₂-R macrocyclic complex shows successive 2 1-electron waves. This difference arises from the flexion ligand. The reduction of kappa 2 to kappa 1 induced the structure change from planar kappa 2 to tetrahedral distorted on kappa 1 state. When this structure change by the first reductions makes the second reduction to occur more smoothly, leading to the second reduction potential more positive. So, one-step 2-electron process was observed on CuDA-Na. On the other hand, CO₂-R macrocyclic complex has more rigid structures, so the second reduction takes place at more negative potentials. So, 2 1-electron waves are observed. Redox-active complex such as ferrocene act as a good marker for monitoring the complexation equilibrium. For ferrocene krypton, the structure is shown in this figure. The complexation of metal ion in the krypton moiety is monitored by using CV. Compared to the original ferrocenes, a new peak appeared on the more positive side when sodium or silver ions are added into the solution. The potential shift of the added metal ions from the original peak potential indicate the strength of the complexation. By considering the square scheme, including complexation and electron transfer in each chemical species, the potential change is related to the equilibrium constant K. Therefore, the equilibrium constant can be calculated by considering the thermodynamic cycles. Hydrogen bonding equilibrium in redox-active complex can be examined by the CV method. When a ruthenium pyridyl benzoimidazole complex show a hydrogen bonding interactions with an heterocyclic base such as pyridine or imidazole through the benzoimidazole imino NH groups. When pyridine was added into the ruthenium solution, a new peak appeared in the negative potential side in addition to the original ruthenium 2,3 couple. And the new peak became larger with increasing the concentration of heterocycles. The amount of the potential shift can be used to determine the equilibrium constant for the ruthenium 3 state by considering this thermodynamic quantity relationship from the square scheme. When original ruthenium 2 state is oxidized to ruthenium 3 state, the K values dramatically increased. In ruthenium 2 state, only 12. However, ruthenium 3 state is 1.2 to to the 10 to the 7th K values. Here is another example for ECEC mechanism. In ruthenium sulfoxide complex, in general, linkage isomerization between S coordination and O coordination mode interchanged by redox reaction of ruthenium. That is, S coordination mode for ruthenium-2 state, but the oxidation to the ruthenium-3 state, the coordination mode is changed to O coordinations. This coordination mode change from S to O coordination can be induced by the redox reactions of ruthenium. Considering this result, dinuclear ruthenium complex with both sulfide and sulfoxide rings ligand has been synthesized, and their CV has been measured as shown here. CV response is a little bit complicated, but we can interpret by ECEC mechanism. The results show that S site in dinuclear ruthenium complex is first oxidized to a mixed balance state at OX1, and then to ruthenium-3 state at OX2 at plus 1.13 volt. Here, linkage isomerization occurred from S mode to O coordination mode in the ruthenium-3 state, and the reverse scan reduction wave at RED1 at 0.57 volt formed a mixed balance state of ruthenium-3 O coordination in the return reductions, followed by second reductions RD2 in this S coordination mix. After RD2, at the ruthenium-2 state, the linkage isomerization occurred from ruthenium O to ruthenium S mode. Thus, a 2-state with hysteresis can be created, which could be used in memory device by write and read out process using molecular hysteresis. So far, we have discussed CV response for E, EC, and EE and ECEC mechanisms. Next, I will discuss electrocatalytic reactions. First, two examples of CV of electrocatalytic reactions are shown here. The first example is the CV of the oxidation of alcohol catalyzed by 2266-tetramethyl-1-piperidine and oxyl, called TEMPO as the electron catalyst. The reversible wave of TEMPO, which initially appeared around 0.5 volt, become irreversible as more alcohol is added, and the current value increased with increasing the added alcohol concentrations, reaching a plateau. In the second example, on the right, reversible wave of 0.35 volt at the modified electrode with fluorescence on graphene oxide becomes a stationary waves with the addition of glucose, indicating fluorescence acts as the electron mediators. As seen in the previous example, the CV feature of the electrocatalyst is that when A is added to the solution of redox pair PQ, the reductant Q reacts with A to form B. At the same time, P is regenerated and PQ pair act as the electron mediators on the electrode surface, catalyzing a reaction that eventually turns A into B. As the concentration ratios of electron mediator P to the substrate A increased, the turnover of the catalytic cycle is accelerated and the current values increased. And when the concentration of substrate is high enough, the current values show a steady state values and give a plateau current. Theoretical study by Sabian et al. Have shown that the shape of the CV of catalytic wave depended on the two parameters. One is lambda, which is the ratio of the reaction rate between substrate and Q to the CV sip rate. Gamma is the another one, is the concentration ratio between the substrate and mediator P. Therefore, the kinetic zone diagram is provided, so from CV shape, we can consider the catalytic activity of the complex. As a first case study, I choose cobalt complex. The ligated cobalt-2, cobalt-1 display a chemical reversible CV response in the absence of substrate at a scan rate of 100 mV, as the dashed line in this figure. However, sequential addition of benzyl bromide with increasing catalytic current as a function of benzyl bromide concentration. This is consistent with oxidative addition of cobalt-1 to benzyl bromide, forming a benzyl radical, simultaneously regenerate cobalt-2 that is reduced as a cathode. By changing N heterobidentate ligand to cobalt-2, the catalytic activity changed dramatically, which derived from the stability of reduced cobalt-1 state. The second example is the cooperative catalytic effect of copper and tempo on the oxidation of primary alcohol studied by Starr using the number of CV technique. The CV response of both copper and tempo gives reversible response, even the triethylamine added. Once alcohol added, catalytic current obtained. So, first, changing the concentration of the copper catalyst, the rate of found to exhibit a first-order dependence on the catalytic current. Similarly, a half-order dependence on the alcohol substrate was observed. With this knowledge in hand, adopting a kinetic framework formulated by Sabian, the ratio of I cat over IP is dependent on the scan rate, according to this equation, where K obs is observed rate constant, so the rate of the oxidation was determined from these equations, which indicate 5 times increased K obs in the presence of copper complex due to the cooperation of two tempo and copper catalysts. The activation and catalytic conversion of small molecules such as hydrogen and carbon dioxide is one of the most important research targets in these days. Recently, many reports have been published for the electrocatalyst, in which the catalytic activity is evaluated by the electrochemical method. I have picked up only one example CO2 electrochemical reduction by cobalt cyclopentadienyl diphosphine ligand with pendant amine residue as a catalyst. CV response of cobalt complex shows two successive cobalt 3-2 and cobalt 2-1 reduction waves at around -1 and -1.3 volt. When the CO2 was added into this solution, the additional catalytic wave appeared at -2.2 volt, which increased with increasing additional water amount. By analyzing these catalytic waves, the turnover frequency 70 to 600 was obtained. In this lecture, I show you several electrochemical reaction pathways such as ECE and ECEC and catalytic mechanism. Cyclic voltammogram include a lot of information as electrode. The classification of CB patterns give us a clue when considering the reaction mechanism as electrode. The catalytic activity of electrocatalyst for CO2 reduction, etc., is evaluated by the analysis of CV response. Here's a reference. If you have some more detailed information, you can read the original papers. Additional note, recently Chemical Communication published a paper on AI technology to let computer interpret CV like this one, which seeks to extract image, features, and numerical data from the shape of the CV and clarify it by deep learning. I still don't understand it, but I introduce it as a paper as a new directions.
Thank you, Professor Haga. If you have any question regarding to the lecture or other topics, you can contact us. In addition, the movie of a variety of topics you can watch here in the BAS channel, which you can follow and have access to the latest news, including the past webinars. The next webinar we are working out to have for next year in February. It will be the fourth lecture in the field of coordination chemistry and electrochemistry. BAS team would like to thank you for having charge with us this year, and we wish you and your family a health, happiness, peaceful, and joyful holiday, and a wonderful new year. For today, thank you, and have a nice week.